for it.
It's more of a geometry question. I feel like I'm getting this wrong a couple times. I don't know how to get you which problem I'm having trouble with.
You can share your screen with me
Okay.
if you'd like. Let
All right.
me show you how to do that.
Okay. Let me go to um I gotta pull up I don't know if this homework is still um like if it was due last night because now on the calendar it says it's not due till the 26th.
Yeah,
It looks like
I meant to push that back earlier. I thought I had, but I hadn't pushed it back far enough, so I literally just changed it a couple minutes ago.
okay.
Yeah,
So
you
chat.
should be able to share with me now. I had to switch it to where it allows anybody, not just me, to share screen.
Okay, let me just
Now, how you do it, I'm not really sure, but with me, I've got a
figure
little button
out
down at the bottom that says share.
how to pull up the Pearson. All right, which one was it? Oh. Um,
Hey, I just looked at my grades. Well, most of my grades are there. For some reason, my chapter 7 stuff isn't on the Canvas.
Yeah, I just noticed that. I don't know if this changed after we were having the problems with Canvas or not, but like chapters 6, 7, and 8 weren't being automatically updated. So I just clicked on that, and they should show in the next, hour or so, hopefully already, but I'm not positive.
Okay.
So hopefully that'll fix itself. I'm seeing your screen now,
okay.
Ryan.
All right. So right here, what I'm having trouble dealing with
Hmm.
is I thought when I drew my free body diagram that the work of gravity on the block would be, I think I had it as mass times uh, gravity over, sorry, no, what I have. So I tried to set up like the work in the x direction for gravity.
Hmm.
Um, and I thought since the work in the x direction for gravity for me would be the hypotenuse, that I wouldn't get negative W sine theta.
Gotcha.
I would get like mass times, what did I get? Mass times gravity over sine theta.
So what's going on there is you have to break down the weight, which is mg, that's a vertical vector that points down,
Yep.
and you have to make a component that's parallel to the incline and another component that's perpendicular to the incline. And what you'll see is that weight, wg, is actually pointing in the opposite direction that the object's going. So when they ask for the work done by the force of gravity, the angle is actually 180 degrees.
Okay.
So it should be mg sine theta for the component that's parallel to the hypotenuse, and then times L, because that's what's parallel to it, and
Yeah.
that's the displacement, times cosine of 180, and that's where the negative comes, or that's a way that you can understand the negative. Another way of
Okay.
understanding the negative is whenever it seems like the force that you're calculating the work doing, when that force seems to be pointing in the opposite direction that it's going, then you should expect it to be a negative work.
Okay. I'm getting the negative. I'm just like the geometric identity, I guess. I'm not getting because I thought that
Did you understand the breaking down of the mg into the vector components parallel and perpendicular to the
yeah,
incline?
so for the opposite, I guess, of the normal force, I was able to get that one. That made sense.
Gotcha. So you are
But
able to do that part.
but in terms of like getting, I don't know. Maybe I just gotta,
You do understand the F is not the work that you're calculating, right? that F that it's
Yes.
shown in the diagram? Okay. So yeah, it has to be the nature of us using the dot product for the for calculating the work is so that you get the component of force that's parallel to the displacement. So once you take that mg vector that points down and you break it into a component that's perpendicular to the incline and another that's parallel to the incline, you see that the parallel one is parallel slash anti-parallel to the displacement. So that's the one that you actually want. So you do W times W meaning mg times sine of theta, and that would be the component of force parallel to the incline, but it actually points down the incline and the object's moving up the incline. That's
Okay.
the fact that they're in opposite directions where you get the cosine of 180. But then you just take that W sine theta and multiply it by L. That gives you the magnitude, and then cosine 180 gives you the -1 that makes it
Okay.
come out negative.
Okay.
Hopefully that helps.
Yep. All right. I'm gonna
No problem.
stop
Well, thank you for
sharing
asking
my
that question.
screen. Thank you. Um,
Anybody else have any questions while we're waiting? It looks like most of you are chatting me your first and last name. That's good. That's what I needed. And we still up. It's actually time to get started. If you can,
how do I stop sharing?
I'm not sure. Wherever the button is that you push it. Well, actually, let me see if I can share. Let's see
Oh,
if
there
it's.
we go. I found
Yeah,
it. Okay, there you
gotcha.
go.
All right. Well, when we last met, I was talking to you guys about conservation of energy. I did a quick little back of the envelope sort of derivation of the potential energy for distances above the surface of a planet that are comparable to the radius of the planet. Whereas when we're talking about a distance from the surface of the planet that is very, very small compared to the radius of the planet, then the potential energy is just mgy. Uh, where y is the vertical coordinate or the coordinate that's perpendicular to the Earth's surface, and you would take y equals 0 to be sea level, say. If you're actually dealing with that bigger type of distance, then you have to use Newton's law of gravity. And for that, what we found out was the potential energy function was negative capital G, capital M, where capital M is the mass of the planet, lowercase m, where lowercase m is the mass of the object whose potential energy you're trying to calculate, and then you divide it by r. So we'll be making use of that in a second, but I wanted to make sure everybody was on board with that. Now what I'm going to do is start off by working some examples, and I'll do so by sharing my screen with you guys. So hopefully this pops up in a second. There it is. Come this way. Feel free to ask me any questions. We can also ask them towards the end of class as well. And then I have another class, for instance, after this one now, I'm meeting at 7:05 with my Physics 100 class after this. So I normally have to make sure I'm finished up by 7. That shouldn't be a problem for you guys. It normally isn't. But anyways, let's start off with example 8.2 from your textbook. This one, I just happened to have time to write it down. What we had learned specifically last time when I went over that sort of mathematical theorem that applies in the case of potential energy functions whenever you have a force that's what we call a conservative force. When you have a conservative force, then there's all these other mathematical anomalies that come out. Specifically, the curl of the force is equal to 0. The integral from point A to point B of f dot dl is independent of the path, and it turns out to be some function of b, meaning point B, minus some function of a, meaning the point A that you started at. And also the integral of f dot dl over any closed loop is always going to be 0. And then there exists a scalar function such that f is equal to the negative gradient of u. And that u function turns out to be exactly what that integral from a to b of f dot dl is. That's actually a difference in that u function. So that u turned out to be our potential energy. So now I'm going to make use of some of that. I'll start off with solution. And this is where I normally just write down what equations I'll be using. I don't commit to memory the quotient rule for derivatives. I just use the multiplication rule, and the multiplication rule is that d by dx of f times g is equal to df over dx times g plus f times dg over dx. So that's one of the things that I will be using. We also know that the force, according to that mathematical theorem I talked about last time, is equal to the negative gradient of u, the potential energy function, and the u, or excuse me, the gradient is a vector operator that we can write as, for starters, it's meant to have something to its right. So I tend to try to leave a break or a space between the triangle and the equal symbol here, because basically something goes in this slot. You can put a dot product with a vector field, you can put a cross product with a vector field, or you can put a scalar function right there. Or it turns out you can also put another del operator there as well. All of those are different things you can do, but the main thing is what we're going to do is say that this vector operator is I hat times the partial derivative with respect to x, leave a space, plus j hat partial with respect to y, leave a space, plus k hat partial with respect to z, leave a space. Again, the partial derivative is nothing more complicated than the regular derivative, except that you've got to pretend that any variables you're not taking derivatives with respect to, in other words, whatever variables in the bottom, that's the only one that is acting like a variable. All the other variables, y, z, c, or whatever, can be treated like the number 4 or the number 2 or something like that. So if it helps you, you can literally throw in a number 2 and a number 3 for each of the variables that you have, and number 3, number 4, number 5, number 6, like that, but just don't multiply them out. Work out the derivative and then replace them back with the symbols. So I'm going to show you a little bit of how to do that. And that's what we actually need to do to compute this force. So force is equal to the negative gradient of u, and that gradient of u is the gradient of negative a over x divided by b squared plus x squared, which I'm going to treat this a little differently. For starters, I'm going to go ahead and pull that negative through and make this positive, and then I'm going to replace that del with the actual operation that we're doing. So I'm going to say I hat partial with respect to x. It turns out that's going to be the only one that actually matters, because you can see there's no derivatives with respect to y, so the partial derivative with respect to y is going to be 0. You can see that there's no derivatives or there's no variable z, so the partial derivative with respect to z is also going to be 0, because basically when you're taking the derivative with respect to y, the partial derivative with respect to y, X is like 4, and A is like 7, and B is like 8, and that's clearly just the derivative of a constant, and the derivative of a constant 0. Same thing happens with the Z variable. So in this case, what I'm going to do is I'm going to put a curly bracket around it, and then I'm going to let you guys realize that the numerator is one factor. Oh, I already did the negative. Let me get rid of that. So the numerator is one factor. So I'm going to say uh, a times x, and then the b squared plus x squared to the negative 1 factor, to the negative 1 power, is another factor. And then I'll say plus j hat 0 times 0 plus k hat times 0 for the reasons I just mentioned to you. So hopefully that makes a little sense. Let's go ahead now and compute it. I can, in fact, pull that a out in front if I wanted to, but I'm going to choose not to do that right now. I'm just going to put the I hat out in front. And now I'm going to take the partial derivative of a times x with respect to x, and then I'm just going to multiply that by 1 over b squared plus x squared, because that is what b squared plus x squared in parentheses to the negative 1 power is. Now I'm going to do the other part of the product rule. So I'm going to instead leave the a times x alone, and now I'm going to take the derivative with respect to x of b squared plus x squared to the negative 1 power. And in doing that, you can see in the first case, the derivative of ax with respect to x is just a. So I'm going to get a, and then, or actually, let's go ahead and make it a little simpler. I'm going to go ahead and write that as a over b squared plus x squared because there's nothing that happens to the other factor. And then I'm going to say plus a times x. That's that first factor that we took the derivative of already, but now I've got to take the derivative of b squared plus x squared to the negative 1 power. The derivative of u to the negative 1 power is negative 1 times u, which of course is b squared plus x squared, to the negative 2 power, times the derivative of b squared plus x squared with respect to x, so that's just 2x. So that is the whole derivative. I'm going to go ahead and carry this out and make some simplifications algebraically. So there's my I hat. Now I've got I hat times a over b squared plus x squared. And now over here on the right, I've got a minus that popped in from the differentiation of u to the negative 1 power. And I'm going to get an ax on top. And then I'm going to get a b squared plus x squared to the negative 2 power. So I'll just put that there. And now I've also got to multiply by 2x. So I'm going to write this as 2ax squared. So now we can get a common denominator by multiplying the left fraction by b squared plus x squared over b squared plus x squared. That's going to become a times b squared plus x squared minus 2ax squared. That's the whole numerator now. And now the whole denominator is b squared plus x squared to the 2 power. Now I can simplify the numerator by distributing. So I get a b squared plus a x squared minus 2a x squared. All of that is going to be divided by b squared plus x squared to the 2 power. So finally I can say the force is actually only pointing in the x direction, and therefore it only has an I hat component. But you can see ax squared minus 2ax squared is negative ax squared. So I'm going to call this a times b squared minus x squared over b squared plus x squared to the 2 power in the I hat direction. And that is the actual function or the functional form of the force. Anybody have any questions on that? Okay.
I want
Well,
to say yes, but mainly because there was so much in there. I think I'm gonna have to rewatch this a couple times because a lot
yeah,
of it was.
sometimes it's a lot of steps in these derivatives. A lot of calculus-based physics textbooks make no apologies about having really long, complicated differentiations. They're a little bit nicer about not giving you really difficult integrations, but that's not the case with differentials or derivatives. So yeah, it just takes a little bit of time. Feel free to use the quotient rule if that makes it easier for you. You're welcome to do that. I just never do it myself. But anyways. We're going to move on now unless anybody has any other questions.
There's a question in the comments.
Okay, let me pull that up real quick. Thank you. Appreciate that. Now, if I can get the chat. Ah, there's the chat. Where did your negative go from the top? Negative AX. So I pulled that out in front early on. So I had a negative as part of the formula to begin with, and then I had a negative there. So when I pulled this negative out in front, it's a negative times a negative gave me that positive. Then I end up getting another one later when I do this derivative. But that's why we ended up getting that negative there. So does that help? Yeah, he got it. All right, good deal. Thanks for letting me know about that comment too, because I always forget to put up the meeting chat down here at the bottom once I switch to sharing my screen. So that helps me. We're moving on now to conservation of energy, and I mentioned already, and I'll mention it again, and your book mentions it several times. There's a couple different ways you can do conservation of energy. The two versions that I've shown right here in the blue box, I'm trying to show you how the second version came from the first version. But initially, the first version is just that if you don't have any forces except for conservative forces, then there will be no dissipative forces, if you will. The dissipative forces would be forces that would steal energy from it, and you can't get it back just by turning around and going backwards. For instance, when you throw a ball up, it goes up, and that's converting kinetic energy into potential energy. But then all of a sudden, you could allow the potential energy to start decreasing, and that would be going back to get the state you were in before, where you had a maximum of kinetic energy and zero of potential energy. That's the way conservative forces act. Whereas if you were talking about air resistance, on the way up, the air resistance is slowing the pin down, slowing it down, slowing it down. So ultimately, it doesn't reach the same height as it did when it didn't have air resistance. But worse, when you drop it back down, or when it reaches the top and starts to fall back down, it's going to be slowed down again by the air resistance, and therefore its kinetic energy will be doubly less high than it was when it left your hand. That's what dissipative and not, i.e., non-conservative forces do. These equations don't really allow you to include those, so I use a different version of conservation of energy, and I just use the same equation every time. I developed it when I was an undergraduate doing a lot of tutoring, and I've just used it ever since. So what I do is take sort of from the second form, the ui plus ki, meaning the initial potential energy plus the initial kinetic energy is equal to the final potential energy plus the final kinetic energy. That's what I'm using here. The version that I use, though, is ui plus ki plus work put into the system is equal to u final plus k final plus work put out by the system plus E loss. Okay, now I want to express something important to you guys. When you use this version, other than using that special potential energy that I just talked about when you're dealing with distances from the surface of the planet that are comparable to the radius of the planet, other than those, all these terms are supposed to be positive. But when you do use that potential energy, it by default has a negative in it. And I'll write that potential energy again down again later so you'll know exactly what I'm talking about as far as that goes. But other than that, you need to make sure you don't calculate a W in and it comes out to be a negative. You're just taking the magnitude of the work put in. And the same thing with work out and the same thing with E loss. Now, this is particularly helpful, but I want to say some things about it. The first thing I already said, I told you none of these terms should be negative unless you happen to be using that weird potential energy function that we have to do when we're talking about, actual spacecrafts leaving the Earth headed towards something as far away, say, as almost to the moon or something. Actually, almost to the moon is a really long way. It turns out that the moon is about 60 Earth radii away from Earth, and we need to use that weird potential anytime we're going anywhere near like even half the radius of the Earth, or maybe even 20% of the radius of the Earth. You need to use that more complicated formula. But in addition to not being negative, except in that case, I want you to know that the WN could represent zero terms, but it could also represent one term, two terms, three terms, four terms, five. It could represent any number of terms. The same thing with the W out and the E loss. I'm going to show you one example that's, I just make it up on the fly, and it turns out to be horrible results where we're having a kid going down a down a mountain on a sled and ends up hitting a wall at hundreds of miles per hour. So it's not a very realistic problem, but it's very instructional. So I'll be using that. But the big thing to remember is there's no wrong answer as to what WN is or what W out is or what E loss is. The main thing is you want to take into a consideration any energy lost or any energy gained by the system. And you can use whatever terms you want to do that. The big thing is if you're putting energy in the system, then you should put it in the work in slot. If you're taking energy out of the system, then you should put it in the work out or the E loss spot. Okay. And there's sometimes where it's patently obvious exactly what work in and work out is and exactly what E loss is. That's the kind of example I'm going to show you next. But the majority of conservation energy problems has all these terms. You can see I've got 7 terms in my version. A bunch of them are going to be zero. That's the beauty of the conservation of energy problems. So let me go ahead and do an example using this version. So I'm going to call this just plain Mr. Younger's example. Now, what we're going to have here is I'm going to have a mountaintop and then a really steep mountain, and then it's going to go to level ground. And then at the bottom of the level ground, we're going to jump into what I would call like a rumble strip, or this is sort of like the I don't know if you've ever driven in the mountains, but if you drive in the mountains, you'll see there's these little ramps where runaway Mack trucks can pull off. That's what this is. It's like you could fill it with sand or something like that, and then it would make things come to a screeching halt very slowly or whatever. That's sort of what this is. And then it stops and becomes frictionless again. But at that point, there's going to be a big sheet of like plywood with cushions on it so that the child on the sled can hit this without being harmed. And in so doing, they're going to compress a spring some really potentially very large distance until it comes to a stop. Now, the way I make the numbers up, we have no idea whether it's going to be fast enough, the sled is going to be fast enough to make it all the way across the frictionful area that I drew with the scribbles. And if it does, then we also don't know exactly how far the spring is going to be compressed. So one of the questions we're asking is what would X be if it actually makes it past the rumble strip? Also, what would D sub X be if it doesn't make it all the way to the plywood? And also, one more question. We want to know just before it hits this, what is V final? So those are the questions we're asked. We're trying to figure out, first off, how fast will the sled be going when it gets down to the bottom of the slope and before it hits the frictionful area. Then, once it hits the frictionful area, does it actually make it the whole way? Well, I've got to define some parameters on this. So, one of the parameters I'm going to define is that this distance right here is capital D equals, let's say, last time I did 50 and that wasn't nearly enough. I'm going to say 100.0 meters is how far it goes to there. And I'm going to say mu kinetic is 0.40 there. I'm going to also say that this spring has a constant given by K is equal to times 10 to the fourth newtons per meter. So this is supposed to be, I didn't write it big enough. Let me write it a little better for you guys. I want the spring constant for this to be K is equal to 1.00 times 10 to the fourth newtons per meter. In other words, 10,000 newtons per meter. Okay. And in addition to that, I have the little sled up at the top. So I'm going to draw the sled. And there's the sled. Little girl with a ponytail getting ready to go down. But her father is giving her a push. And the push he's applying is a force of 100 newtons. And he's going to do it over a distance of 3.00 meters. And I'm saying the force is parallel, as is the displacement, so there's no angle between them. I will say that this purple surface is frictionless. That's everywhere from here all the way up to here. And then here as well, it's frictionless. Okay, so that's what those little blue arrows are meaning under that. That's all frictionless. So you can see what I'm wanting to solve for. I want to solve for the velocity she has just before she hits the frictionful area. We're going to solve for then if the actual frictionful area is strong enough to slow her down to a stop. We want to know how far across the frictionful area she's going to make it before she comes to a stop. But if we find that it's not long enough to bring her to a stop, then we're going to say, okay, well, it's definitely going to come to a stop when she hits the plywood that's spring loaded. And in that case, we're wanting to figure out exactly how much compression of the spring occurs to bring her to a stop. So that's what we're going to solve. I will call these, for instance, part A, part B, and part C, even though in some sense there's no part C unless part B turns out to be that it makes the whole way. So it's a little misleading to do that, but I just wanted to give you some indicator. So for starters, I'm going to start with part A, and I'm going to use my equation that I just taught you. That's U initial plus kinetic energy initial plus work in is equal to U final plus kinetic energy final plus work out plus E loss. Again, you can have multiple terms for E loss. You can have multiple terms for work out. You can have multiple terms for WN. The main thing is you want to take into account each thing that steals energy from the system by putting them in the one WN term, and there might be multiple ones, and you want to make sure you only count each one once. And then any of them that are actually, excuse me, that's the ones that are putting energy into the system, goes into WN. And any of them that are taking energy out of the system, you either need to put it in the work out category or in the E loss category. And it doesn't matter which one, but again, you need to count them each one exactly once. So the other thing, I didn't actually put this, so might need to now. I just completely forgot to list this. I'm going to say the height of this hill, H, is equal to 300.0 meters. Okay, I just didn't list that before. What we'll be using though is the potential energies that we've learned about. I'm not using the negative one that I told you about, but U is going to be mgy. K is going to be 1/2 mv squared. And we're also going to use, you could use this as W or U is equal to 1/2 kx squared as sort of the work done or the energy lost by compressing a spring. So we're making use of that. I will tell you also that the little girl with the cart, with the sled, has a total mass of 75 kilograms. So M is equal to 75.0 kilograms, like that. Now we can put in our information. Uh, by the way, when the father pushes the daughter, he's going to push her about 3 meters with a force of 100 newtons, which is really only about 25 pounds. She will actually technically pick up a little bit of speed, but we're going to ignore that. We're going to assume that really doesn't make an appreciable amount of speed. So we're going to take the very initial. Well, that's one way of looking at it. Another way of looking at it is I'm just studying it uh, from the instant it leaves, and then some work is done to it by the father, and then of course she has a little bit of speed, and then she goes down the hill and picks up speed. So, with that in mind, we're going to say the initial kinetic energy is zero. And what I'm trying to do here is just figure out what V final is. So, V final is equal to question mark. Now, with that in mind, since I drew this red line that's supposed to be the same height as the flat ground below, even though I've made it a little crooked, since I drew that way, what I'm trying to tell you is that the y is equal to zero on the flat part at the bottom. And since the kinetic or the potential energy is mgy, the potential energy at the bottom will be zero. So I'm going to call that zero right there. Not only that, when I go up to point A, where the V final is, I'm not going to have done any work or taken any energy out of the system by doing work or by energy loss. So that's going to be zero, and that's going to be zero as well. So with that in mind, I get MGY, which is going to be 75. Ooh, let me write it back in the color that we were working. It's going to be 75.0. I'm going to leave the units off, but you can see that would be kilograms times 9.80 meters per second. So those two give you newtons times 300.0 meters. So that gives you a newton meter, which is a joule. We're going to say the work in this case, since the force is directly parallel to the displacement, it's just going to be 100 0.0 newtons times 3.00 meters. So again, that's a newton meter, which is a joule. That's our work in term. Now we're going to say that's equal to just 1/2 of 75.0 times V final squared. And this will give us our actual velocity at the bottom just before she hits the frictionful area. So if I multiply 75 times 9.8 times 300, I get 2.205, which is one extra sig vig than we need. And that's times 10 to the fourth, or excuse me, times 10 to the fifth joules plus 300 joules. And then that is equal to 1/2 of 75 is 3750. So 37.50 times V final squared. So that gives me V final is equal to the square root of. Now I'm going to take the 2.208. That's what happens when you add the 300 to the 2.205. That's joules, by the way. Oh, and I also forgot to times 10 to the fifth. That's joules. And then we're dividing that by 37.5. In this case, it's kilograms. Now, a joule is a newton meter, and a newton is a kilogram meter per second squared. So a joule, which is a newton meter, is a kilogram meter squared per second squared. If I divide that by a kilogram, I get a meter squared per second squared, which is exactly the unit that we want, because when I take the square root of a meter squared per second squared, I get meters per second. So I'm going to take the 2.208 and I'm times 10 to the fifth, and I'm going to divide that by 37.5. And that gives me 5,888 meters squared per second squared. And taking the square root of that by raising it to the zero point 0.5 power, I get 76.73 meters per second, which is literally on the order of a couple hundred miles per hour. So it's a really high speed, and of course potentially dangerous, right? But again, I'm just making this up as an instructive thing, so we'll be able to see in what sense could we use these terms, or in what sense did I, the person that made up this goofy form of the conservation of energy equation, in what sense did I mean these terms? So now I've done that. Now all I got to do is figure out exactly how much energy is lost from the friction. So for instance, if I were to actually assume the girl hits that frictionful area and goes the whole 100 meters, how much energy is lost? If that energy is less than the 2.208 times 10 to the fifth that we just found, then we know that she's not going to make it the whole distance across the 100 meters. But if it's less than the 2.208 times 10 to the fifth joules, then we know she's going to make it the whole way. So let's do now part B. So E loss, and I'm writing total here just because I'm saying what would the E loss be if, in fact, she went the total distance of 100 meters. So in that case, this would normally be something that would be a negative amount of work because the friction force is pointing this way, she's moving that way. Therefore, you'd get a negative quantity. But we only take the magnitudes of work and energy in these equations. That's why I said it's always going to be positive. So in this case, I'm just going to take the force, which is the friction force, times the displacement, which I call D. But the friction force for kinetic is mu kinetic times the normal force. But it is horizontal, so the normal force should be exactly equal to mg. So this is going to be mu kinetic times m times g times d, and therefore we're going to get 0.40 for the coefficient of static friction times mg, that would be 75.0 times 9.80. Notice the 75 times the 9.8 gives us newtons. And then the D is 100.0 meters. Oops, didn't mean to put a meter on there. 100.0. That gives us newton meters, which is in fact a joule. So now I can multiply this and say zero point 0.4 times 75 times 9.8 times 100. This gives me 29,400. And I only technically have two sig figs here, so that's not a sig fig either, and that's joules. And we could call this 2.940 times 10 to the fourth joules, which is clearly way less than 2.205 times 10 to the fifth. So let me write this in a different color just so you'll know I'm trying to point out something different. 2.940 times 10 to the fourth joules is way less than 2.208 times 10 to the fifth joules. It's a factor of 10 bigger, basically, almost a factor of 10 bigger. Therefore, the sled clears the frictionful area. So we know it's going to make it past there, so B is not really a point, okay? Now the next thing we're going to do is we know exactly how much energy is going to be drawn out, and therefore we call it E loss by the friction area. So I can just fill that in as the 2.9, or excuse me, the 2.94 times 10 to the fourth. And now we're going to use the exact same equation we had before, only now we're doing what we called part C. So now we have U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. Now, in this case, we're actually allowing the girl to completely hit the plywood with the cushions on it and compress the spring until the spring brings her to a complete stop. That means the final kinetic energy is zero. We already talked about how the height at the bottom would be y equals zero, so the U final is zero. The kinetic energy initial, since we started it at zero and then the father pushed it, that means that's going to be zero. So now all we can do is fill in the rest of the stuff. We know what the left hand side is. The left hand side is going to be the 2.208 times 10 to the fifth joules. That's the UI plus WN right there. Now we also know the E loss, and what we have to do is figure out the workout. Now, in this case, the workout is going to be the work done in compressing the spring. So it's going to be 1/2 times 1.00 times 10 to the fourth. That's newtons per meter times x squared, where x is going to be the amount of compression that the plywood and the girl put on the spring. And then the E loss is just going to be that quantity we just calculated, which is 2.940 times 10 to the fourth joules. So I can take the 2.208 times 10 to the 4, or 10 to the fifth, excuse me, and I can subtract from it 2.94 times 10 to the fourth, and that's going to give me 1.914 times 10 to the fifth joules is equal to 0.500 times 10 to the fourth times x squared. So x is going to be equal to the square root of 1.914 divided by, that's 1.914 times 10 to the fifth, by the way, joules divided by, remember the K is newtons per meter, so this would be 0.500 times 10 to the fourth newtons per meter. When you divide a joule, which is a newton meter, by a newton, that's going to give you a meter. And then when you divide it by a newton meter, that meter is going to come on the top and give you meters squared. So we can now say this is divided by 0.5 times 10 to the fourth. And this gives me the square root of 38.28 meters squared. So now I'll take the square root of that by raising it to the 0.5 power, and that gives me 6.187 meters. Now, obviously, that's a crazy idea. Just imagine pushing a spring that compresses 6 meters. That's, about 20 feet, a little bit more than 20 feet. So that is not a physically reasonable problem. But the more important thing to realize here is now we've sort of, in some sense at least, figured out exactly what we can use the work in, work out, and E loss terms for. There's a lot of other choices, but this gives you a pretty clear display, or at least example of one way you could use it. Does anybody have any questions on that? Now, one of my students in the face-to-face class today, she mentioned, remember this girl is going to run into this plywood. She's going to compress the spring. Now, what normally happens is the spring then springs back out. Well, you can now go back if you wish for an extra credit, and you can calculate exactly how far up the mountain the girl would be slung by the spring because she's now compressed it by 6.187 meters. So you've got an amount of energy equal to 1/2 times K times 6.187 squared. That's going to go into launching her at some speed. You could figure out exactly what speed she'll have just as she enters the frictionful part. Then you can calculate how much energy she's going to lose from the frictionful part. And then you can figure out how much potential energy she can gain to go back up the mountain. And you might find that she's going to go a very large fraction of the 300 meters in height. If you want to work that problem, just write it out. Start off with this part using these results and then calculate how high she'll go back up from the spring pushing her back. That's just an extra little problem you can do if you want, but you're not required to. Anybody have any questions on that? All right. So that was another example for me to show you regarding how we could go about doing conservation of energy. I'm going to solve a few more problems, one of which I want to solve using that potential energy function that I derived last time. So let me start off by writing those potential energy functions as well. So we've got U is equal to a potential energy, and that could be given by mgy. And as we saw earlier, it doesn't matter what you consider y equals 0 to be. Last time, remember, we worked that problem with the roller coaster. And in one case, we worked it as if point number 1 was a 0 of potential energy. And then we found the change in potential energy from point 2 to point 3. Then we worked it again using point 3 as the 0 of potential energy and found the change in potential energy from point 2 to point 3. And lo and behold, they were exactly the same values. That is what's relevant. The change in potential energy is what is relevant, and because of that, you can add any arbitrary constant to mgy to get a new value of u. Because that constant, when you do a difference or a change in it, will be in both terms, the final one and the initial one. So the final one will have subtracted from it the initial one. So that's perfectly reasonable and it's easy to do. And it's sort of a simplification of a bigger part of physics that we sometimes do, where we just find that you only need to determine something up to an additive constant. In the case of the electric and magnetic field from Maxwell's equations, we only know the divergence and the curl, and that only gets us a vector field up to an additive vector constant. So that's another case. More generally, there's a thing called gauge invariance that allows another change of something that's completely irrelevant. So that's really what this is about. There's a lot of different ways where certain terms could have additive constants to it, and it's not going to bother us in understanding the physics. So that mgy is with any particular origin that you wish to choose. You could also say U, the potential energy, is what you get when you store energy in a spring, but you could also call that work, like I just finished doing myself. So I'll put that as U RW is equal to 1/2 kx squared. We also have U is equal to negative g, the gravitational constant, m, the mass of the, say, planet that's causing the potential energy, the mass m of the object that has the potential energy, divided by r. That's that more general potential energy for values that are comparable to the radius of the Earth. And then we also have kinetic energy is equal to 1/2 mv squared. Once we cover rotational motion, you'll find that there's other terms as well. There's kinetic energy associated with an object moving left or right or up or down or in or out. Those are all in 1/2 mv squared. But there's also one associated with it rotating about some point, and that one turns out to be a 1/2 I omega squared, which we'll learn about later. Now, now that we have all that, what I want to do is calculate what would the radius of a planet be if its escape velocity was the speed of light? C. That's the symbol we use for the speed of light. Okay. So what I'm going to do is, oops, I'm going to try to draw a better circle than that. I'm going to draw a circle to represent Earth or some planet in general. The radius of that planet is going to be big R. Okay. And we're going to imagine a spacecraft sitting on the Earth with or on the planet with a mass m. And what we're going to imagine is it takes off with such a large speed, v initial equals c, such that it goes infinitely far away, and then just as it reaches infinity, the final velocity is zero. Okay? That's the definition of escape velocity. You could actually find that the velocity has to be that big or larger. And if you found that it was larger, then when it reached infinitely far away, it'd still have some velocity left over, therefore some kinetic energy left over. So what I'm going to use to solve this problem is conservation of energy. And my conservation of energy says U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. Now, this is obviously a huge simplification because obviously there'd be a butt ton of air resistance in getting out of our atmosphere. But that being said, the atmosphere is very, very thin compared to even the radius of the planet, much less the distance to infinity. But still, we are making a big assumption here. I'm assuming that no energy is being put in. We're just basically treating this mass lowercase m as if it's a projectile. So we're imagining shooting it at the speed of light, and it doesn't have any ability to get any energy later via thrusters or anything like that. So what that means is work in is going to be out, is going to be zero. We also are going to reach infinity. And at infinity, that was specifically what we chose to let the zero of potential energy be. And that's why that negative sign is in there. So at the end, the potential energy is going to be equal to zero. And because we're just looking for the escape velocity, which is the velocity that it would have at the instant or excuse me, the velocity that it would have, so that at the instant it got infinitely far away, its velocity would be zero. And since the velocity is zero, that means the final kinetic energy will be zero. Uh, in addition to that, we also have the work out. We're not actually compressing any springs. We're not doing any work against anything. So that's going to be zero. And we're ignoring any energy losses. So that's going to be zero. So lo and behold, what do we get is negative G big M, that's the mass of the planet, times little m divided by the radius of the planet plus 1/2 m. Now, this time instead of v, we're using c, and that's going to be squared, and that's equal to zero. In reality, just in case y'all don't necessarily understand this, this is the limit as r approaches infinity of negative g m m over r, which I think you see is equal to r. So that's what really happened to that first term on the right. Now I can solve for r by taking the negative term and putting it on the other side. So I'm going to get 1/2 mc. Oops, I didn't mean to write this in blue. I mean in red. I meant to write it in blue. So I'm going to say, uh, oh, for starters, I can also divide through both sides by m. Obviously, I'd get
Uh,
0 on the right. Yes, sir.
I was just wondering if the escape velocity always ends with the initial being some number, but the final velocity being zero. Does that mean the acceleration is always negative?
No, it just means that the energy is always going to be negative. The total energy is always going to be negative because we've set 0 at infinitely far away, and there's no way you could get smaller, or excuse me, bigger than 0 away. So, or bigger than infinity away. So, the biggest potential energy you could possibly have if you reach to infinity would be 0 as it's defined at that point. I don't know if
Okay,
that helps your question, but that's what's going on here. Does that make sense?
a little.
Okay. Uh, All right. Well, yeah, mull and stew on it a little bit and think about it. I don't know why I wrote that all in blue. I mean, all in purple. I wanted to write it in blue. So, when I divided through by m the mass of the spacecraft that's trying to have this escape velocity canceled out. And that's good because this tells us that the escape velocity for a particular planet to reach for it to be the speed of light doesn't depend on what the mass of the object will be. So as I said, I'm going to pull the negative side to the other, the negative term to the other side, and this is going to be 1/2 c squared is equal to gm over r. And what we were asked is what would be the radius of the planet if the escape velocity was the speed of light. So basically, we're saying, hey, how small would a planet need to be for Newtonian gravity to create a black hole? Because what we're saying is only, if anything, only a speed of light could actually escape the planet. In reality, a black hole doesn't even allow light to escape it that way. So this is sort of the asymptotically approaching value that it could be to just barely become a black hole. So, with that in mind, we get that r, the radius of the planet, is going to have to be 2gm over c squared. So, that is the radius that the planet would have to have. And in fact, that's called the Schwarzschild radius. Hopefully, I'm spelling that right. That's not my native language, but Schwarzschild radius. The neat thing about this is we've done this with Newtonian physics, but we managed to get exactly the right result that general relativity gives us. If you work the same problem out with general relativity, you would find that the Schwarzschild radius, the radius that we use for a Schwarzschild black hole, is exactly this quantity. And to give you some idea how big it is, let's do a calculation to figure out what the Schwarzschild radius for the Earth would be. That's 2 times 6.67 times 10 to the negative 11th. That's Newton meters squared per kilogram squared. That's the units of G. And then we've got to take the mass of the Earth, which I wish I knew off the top of my head. I forgot it for a second, but I've got plenty of ways to get it. I want to say it's 7.09 times. Nope, I was completely wrong. I was remembering something else. So this is 5.97 times 10 to the 24th kilograms. And then I got to divide that by the square of the speed of light. The speed of light is actually quite a bit bigger than this, or quite a bit more complex than this, but to 3 sig figs, you can pretty much call it 3.00 times 10 to the 8th meters per second. That's 300 million meters per second. It's also 186,000 miles per second. So that gives you some idea of how big this is. Let's go ahead and calculate it. I'm going to say it's 2 times 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24th. That's my whole numerator. That gives me 7.96 times 10 to the 14th. Kilograms, that'd be Newton meters squared per just kilogram, not kilogram squared. And then this would be divided by 3 times 10 to the 8th squared gives me 9 times 10 to the 16th, which obviously we didn't need our calculator for that. And that's meters squared per second squared. And you can see that that ultimately gets rid of everything but one of the meters. So I'm going to say 7.96 times 10 to the 14th divided by 9 times 10 to the 16th gives me 0.00884 meters, which, if you wanted to convert this to millimeters, it would be 8.84 millimeters. So about the width of my pinky nail. That's how big the Earth would have to be if it was going to be a black hole. Assuming I did all the calculations right, which I seem to remember a slightly different number, but that looks pretty right. If I remember correctly, for the Earth, I mean for the Sun, it has to be on the order of a few kilometers, like on the order of 10 kilometers for the sun to be a black hole. So you can do the same calculation substituting the mass of the Earth, which by the way is 2 times 10 to the 30, 2 times 10 to the 30th kilograms. And in that case, you're obviously going to get a factor of a million bigger. And you can see that that would be on the order of kilometers, not the order of meters or millimeters. Anybody have any questions on that? All right, so that was a example again of using conservation of energy. You could also, for instance, just find out what the escape velocity would be by solving for v, and assuming you started on the radius of the planet. In that case, you'd end up getting a formula for the escape velocity, and that escape velocity would in fact be the square root of 2gm over r. So I'll just write that down here. V escape is equal to the square root of 2gm over r, where r is the radius of the planet. So that should actually give it to you as well. But that's another thing you can do with conservation of energy. Anybody have any questions on that? All right. Well, we're going to work a couple more examples. Let's do example 8.2, I believe it is, 8.3. Example 8.3 says, if the original height of the rock is y1 equals h equals 3.0 meters, and they're referring to a figure I'm going to draw for you in a second, calculate the rock's speed when it has fallen to 1.0 meters above the ground. So what we're saying is y2, or y1, excuse me, is equal to, they call it h as well, so we'll say that's h, which equals 3.0 meters. Y2 is going to be a height of just 1.0 meters. I'm doing 3 sig figs just for the heck of it. And what they want to know is what's the rock speed? V2 equals question mark if V1 was 0, because that's part of the problem. They were imagining the a rock was just dropped. So we'll imagine this is our rock, if you will. We'll imagine this is our y-axis, this is our x-axis, and we'll imagine that this part right here, actually I don't want to do that part. I'm going to say this part right here is 3.00 meters, and that's equal to y1, and y2 is 1.00 meters, like that. So we're going to take U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss And like I said, as you get practice, you'll know when you're not going to be using these work in, so you won't even take time to write those, but it's nice to have them when you need them. So right now, for instance, we're not going to be putting any work into it. We're not going to be getting any work out of it, and we're not going to lose any energy to E loss. And if we were actually allowing the rock to meet the ground, we wouldn't even have a U final. The U final would be zero, but in this case, we can't do that. But we can say, since we dropped it from rest, that the initial kinetic energy is zero. So what we end up getting is M times G times Y1 is equal to M times G times Y2 plus 1 half M V2 squared. Now, you can automatically see right now that clearly I can divide both sides by M, and that's going to disappear. The M's will disappear. And from that, we can get G times Y1 minus Y2 is equal to 1 half V2 squared. So we finally can say that V2, actually, I don't like the way I wrote that. We can say that V2 is equal to the square root of 2g y1 minus y2. Now, I'm going to go ahead and calculate that, but I want to point out exactly what that's telling us because it's a very interesting thing about physics that I love. So I'll do that in a second, but we'll take the square root of 2 times 9.80 meters per second every second times y1, which is 3.00 meters, minus 1.00 meters, which is y2. So you basically see that you're getting 4 times 9.80 under the square root, and that has units of meters squared per second squared. So when you take the square root of that, you're just going to get meters per second. So I'm going to take the square root of 4 times 9.8, and that gives me 6.26 meters per second, and that's V2. Okay. Now, I want to point out that this is exactly what you would have gotten if you did this with kinematics instead of doing it with conservation of energy. The kinematics would allow us to use the equation V squared is equal to V initial squared plus 2A x minus x0, like that. And in this case, you would have the initial velocity being equal to zero, and you would actually have the acceleration being in the negative direction. So you would get this quantity negative 9.80, and that would actually make up for the fact that this x and this x have been reversed in my problem. And when you went to solve for the final velocity, you'd get v equals the square root of 2 times g times y1 minus y2. Notice it's initial minus final instead of final minus initial, and that's just because the negative in the G would have canceled out. So, isn't it amazing that doing it entirely different ways, we used the conservation of energy to derive a equation for kinematics, basically. Anybody have any questions on that one? Okay. There's a conceptual example, 8.5, that I want to discuss with you, so I'm going to do that now. Well, that was helpful. So what we have here is two water flume paths that are supposed to be the same length. So those two red lines are both supposed to be the same length. And even though they look like they're slightly different heights at the end, they're actually not. They're supposed to be the exact same height at the end. And one of them has Paul sliding down it, and the other one has Jeannie sliding down it. And what they're asking is which rider, Paul or Jeannie, is traveling faster at the bottom. And then part B, which rider makes it to the bottom first. So A, which is faster at the bottom, and B, which gets there first. So for starters, as far as which goes to the bottom, using conservation of energy and ignoring air resistance and all that, we can basically just reduce it to U initial plus K initial is equal to U final plus K final. But in fact, the K final, the U final is going to be zero and the K initial is going to be zero. So we're going to get mg y is equal to 1/2 mv final squared. So you can see since the y's are the same and the masses don't matter, then clearly the final velocity is going to be the same in each case. So A, the answer is neither. They will have the same speed. Okay. And then for part B, they want to know which one gets there first. Well, notice that the way Jeannie's path is, she immediately starts falling downward. So what's happened is she's lost some potential energy way before Paul lost his potential energy. Well, it's a zero sum game. So if you lose potential energy, that means your kinetic energy goes up by the exact same amount. So that means Jeannie is not only lower, which makes her closer to the bottom, but in fact, she's lower and she's going faster. And at every point, she's going to be lower. So at every point, she's going to be going faster. Therefore, she will get there first because it takes her less time. Again, remembering that the length of the two is the same. So Jeannie gets there first. Anybody have any questions on that? All right, so that's a kind of neat problem. I think the rest of these are pretty straightforward, especially compared to the more complicated conservation of energy problems I just did. There's a nice little pole vaulter problem that you can work on. That's pretty straightforward. There's a dart gun. Just in the case of a dart gun, imagine a dart gun where you take, it's like one of those toy guns. You take a little dart and you press it against the spring mechanism inside of the gun. And then inside of there, there's a little spring loaded catch that catches the spring once you push it back. So it keeps the spring completely compressed. So you put in a certain amount of work to compress that spring with the dart up against it. That work is now transformed into potential energy of the spring. And that potential energy, once you pull the trigger, will immediately turn into kinetic energy. So it'll start to speed up the dart, speed up the dart, speed up the dart. And just as it reaches the spring reaches its equilibrium position, it'll start to slow down a little bit and the dart will separate from the actual spring and the dart will achieve a kinetic energy that happens to be about exactly equal to the 1/2 kx squared that the spring had. Now, if the spring actually had some mass, that would steal some of it because some of the potential energy that the spring had is now going into the spring going wee like this. That would lose some. But if you ignore the mass of the spring, then all of the potential energy that the spring had will be converted to kinetic energy of the dart. But you're also, of course, ignoring air resistance and friction, which probably is not that bad of a thing to do in most of the problems because normally you're going to go much, much faster. And the friction force is going to be so small and the air resistance is going to be so small that it shouldn't matter. So in that case, even though you have that long conservation of kinetic energy, UI plus KI plus work in is equal to UF plus KF plus work out plus E loss, even though you have all that, you're really just going to have 1/2 KX squared is equal to 1/2 MV final squared. In this case, the mass does matter. So you can solve for the kinetic energy, or excuse me, solve for the final velocity, but you definitely have to have the mass and the spring constant. So hopefully that is good enough to help you better understand 8.6 and 8.7 for that matter. 8.8 is another fairly trivial one. 8.9 is kind of complicated. Let's do 8.9. So I'm going to say example 8-9. It says a simple pendulum shown in figure 814 consists of a small bob of mass m suspended by a massless cord of length L. The bob is released without a push at t equals 0 where the cord makes an angle theta equals theta 0 to the vertical. Describe the motion of the bob in terms of kinetic and potential energy, then the speed of determine the speed of the bob as a function of position theta as it swings back and forth. And C, at the lowest point of the swing, find the velocity. And in D, find the tension in the cord Ft, ignore friction and air resistance. So that sounds pretty complicated. Let me draw the figure. It won't seem quite as bad as it seems right now once you've seen it done. So this is going to be vertical. We're going to say that this is the length L, and I will indicate that by drawing a little line here and a little line here and saying this is L right here. And that's to the center of mass of the bob, whose mass is M. And we're going to say the angle here, the angle that it's making with the vertical is theta 0. And what we can do is we can immediately start to make some geometric sense out of this diagram by realizing that this distance from here to here is L cosine theta 0. And in fact, what's going to happen is this object is actually going to go back and forth like that in time, and it shouldn't be able to reach any higher than it was beforehand. So this should also be an angle theta 0. What I'm going to do is work out what the potential energy is. I'm going to use UI plus KI plus work in is equal to U final plus K final plus work out plus E loss. This is another case where the E loss, I'm going to ignore the work out, I'm going to ignore the work in, I'm going to ignore. And in fact, since we're starting at rest, the initial kinetic energy is 0. And if we consider theta equals 0, the final, then U final would be 0. But I'm not doing that right now because I want to be able to find out the velocity as a function of theta. So the potential energy is actually given by this little quantity from here to here, which is H. And the bigger quantity from the ceiling all the way down to the bottom of the purple arc is L. So what we see is that this distance from here to here is L, and this distance from here to here is L cosine theta. So if I subtracted L cosine theta from L, that would give me H. That means I am going to say M times G times parenthesis L minus L cosine theta initially is in fact theta 0. Now that's equal to mg. I'm going to go ahead and factor out the L this time and say that's 1 minus cosine theta, and then plus 1 half mv squared, where v is the velocity that it has when the angle is theta. You can immediately see here that the m's cancel out again because there's a m and an m everywhere. You can actually distribute a little bit and get G times L minus GL cosine theta 0 is equal to G times L minus GL cosine just plain theta. Now you can see that I could subtract GL from both sides and that'll disappear. And then we're also still going to have the plus 1 half V squared. So I can pull the GL over to the other side, or actually I'll pull the V to the other side, and I'll get 1 half negative 1 half V squared is equal to G times L times, now it's going to be cosine theta minus, or in this case, since I'm bringing it other to the other side, ooh, I got to reverse it. So this is going to be, when I bring it over to the other side, it's going to be theta 0 is going to be the positive one, and the cosine theta is going to be the negative one, like that. So we can see V is going to equal the square root of 2GL times cosine. Now, if I take account of this negative, I'm going to have to switch the order of that and say it's cosine theta minus cosine theta 0. Oops, minus cosine theta 0. And what you can see is that clearly this is going to wobble back and forth, if you will. And if you wanted to know exactly what the velocity would be at the bottom, which would be its fastest, that's when theta equals 0 degrees. And cosine of theta, cosine of 0 is equal to 1. So V at the bottom would equal the square root of 2GL times 1 minus cosine theta 0, like that. So we've now figured out a general expression for the velocity as a function of time, as a function of angle, and we figured out a velocity at the bottom. And I didn't find the tension, but this is close enough. I know the time is up, so you guys are free to go. I'll wait for the last person to leave in case anybody has any questions, but make sure you chat me your first and last name and have a good one, everybody. Oh, don't forget there is a practice test I posted as well as a online test that's been posted, and we're shooting for a face-to-face test that will happen sometime over next week through next weekend. Not this coming weekend, but the weekend after.
I have a quick question real quick.
Yeah, is that a helmet, John?
Oh yeah, it's
That's cool.
my
Motorcycle helmet?
no, it's like my favorite F1 driver's helmet.
Oh, okay, cool. I thought it
Yep.
was a rock for a second there because it looked all
No.
fancy up, but that's cool.
So
Go for it.
are we gonna have the same like from the previous face to face, are we able to like take it like around the same time as well? Like
Yeah,
would
yeah, I'll
your
give you at least one weekend and 5 weekdays for you to schedule it, but I would sometimes even give you 2 weekends and 5 weekdays.
Okay, yeah, because I have a friend that's like in your in-person class, and I
Mhm.
think because I asked her, I was like, "When are you guys taking it?" She said November 5th, and I was wondering if we're able to take it like that same day.
Yeah, you could do it that same day. It might be a little earlier than you'd want to, but you're definitely welcome to do it that day.
Okay, cool. Because last time I took it was it was like at the end of their class, like around 2 p.m. Like, will it be the same
Yeah,
for
so I've got a physics 242 that I think is meeting November 5th, but the way this class, the 241 class is, I think our final, or excuse me, our face-to-face test is on the 29th, which is a week from today. But you would have, that week plus the weekend and probably a couple days thereafter. But you could definitely take it on the day that I do it, which I think, like I said, I'm pretty confident it's on the 29th, which is a week from today.
Okay, yeah, cool. Because on the syllabus it said the test is due no later than November 2nd. So
Yeah, yeah, that sounds like what I would normally plan on doing.
okay, sounds good. Thank you.
All right, thanks, John.
Yep. Bye bye.
You see ya. Ryan, did you have any questions?
Yeah, I just got one last question. The chapter 7 homework, so the schedule for the Canvas says it's due on Sunday or
For
26th.
for what are you asking about the homework?
Chapter 7 for homework.
Okay.
But mastering physics is telling me it's due yesterday, so I just want to know if I need to lock in and finish it
No,
out tonight.
I recently just changed the scores. I mean the dates. Let me tell you exactly what they are. I changed them just before class came. Uh, for chapter, you said chapter 7 or chapter 8?
Chapter 7.
Okay. Chapter 7 was technically due on the 21st,
Okay,
but
I have one problem left, so I can just
I
finish
think
it.
I'll give y'all some extra time on that. So I'm gonna give you at least 2 more days on that one. Let's change it
Yeah,
right
there's
now.
just one hard problem towards the end that I was having trouble with the
Ah,
pendulum,
what
but
the
I didn't
heck?
want
I'll just make it to the 26th then.
to
Feel free to
appreciate
drop
it.
me a text message.
Yeah, I
About
just didn't know if I could ask about problems that are like
yeah,
graded.
you absolutely can. What I try to do is when somebody asks me about a homework problem or a practice test, I try to ask them leading questions so they can figure it out. But I'm completely cool with helping you.
Okay.
So for the record, while I've got it on video, I've changed the chapter 7 homework and the conceptual to be due on October 26th, and I've changed the chapter 8 to be October 28th. That may or may not go a little later, but I did finish chapter 24 today, so that should be, I mean, chapter 8 today, so that should be done.
Okay. Thank
All
you.
right, no problem. You have a good one.
You too.
All right, well, it looks like we're about done, so there's nobody else here. Have a good one. Bye bye.